In this video, let's examine function block diagrams including delay blocks, pulse timers, mathematical operation blocks, and counter blocks. First, let's start with the delay blocks. There are various types of delays such as on delay, off delay, on and off delay, retentive on delay, and timer output relay. We can define the delay time within the block in milliseconds, seconds, minutes, or hours. We can also assign values externally via AT input depending on the unit selected. The priority is always based. Let's consider the working logic of the blocks with examples. For the sample application, we connected digital input 0 as a trigger input and started the simulation. When digital input 0 is active, it will initiate an on delay. We have set all durations to 5 seconds. It will wait for 5 seconds in on delay and will switch to position 1 after 5 seconds. In off delay, as soon as digital input 0 is active, it will switch to position 1, but when digital input 0 goes to position 0, it will wait for 5 seconds and then switch back to position 0. The on and off delay will provide delays both when rising and falling. Retentive on delay will wait 5 seconds after digital input 0 becomes active, switch to position 1, and will maintain position 1 even if it drops back to 0 until a reset input receives a The timer output relay will activate as soon as digital input 0 is active and will revert to 0 at the end of the set duration if the trigger input is still. Next, let's look at the pulse timer blocks. We'll start with a symmetrical pulse generator. You can enter the period duration in milliseconds, seconds, minutes, or hours, or set the value. In this simulation, let's look at setting the value externally. In the symmetric pulse generator, it toggles low and high at half the period duration. Therefore, if you want to generate a pulse per second, you need to enter 500 milliseconds. Let's start with this example. When I activate digital input 1, it will start at position 0 for 500 milliseconds, then switch to 1, 0, 1, and continue generating pulses until a signal is received at the active input. We activated the enable input, and it started generating a pulse per second. We can increase this period. If we want 2 seconds, I can enter a value of 1000 milliseconds. This way, it will generate a pulse every 2 seconds. We can increase or decrease the period duration like this from outside. And when we set digital input 1 to position 0, it will stop generating pulses. The real-time pulse generator, on the other hand, generates a pulse every second or every 3 seconds. This block does not function in the simulation. Therefore, I loaded the project onto the device and connected via USB or TCP to observe it live. The real-time pulse generator will generate a pulse every 3 seconds. You can connect the trigger unit entered in Modbus communications to the real-time pulse generator or symmetric pulse generator if you want to perform regular data. Next, let's look at our mathematical operation blocks. First, let's start with comparator blocks. We have blocks for word, analog, and long data types. Here, what operations can be performed? We have options such as comparisons within a range, greater than, less than, outside the range, equal, not equal, less than or equal, and greater than or equal. We can enter For our first application, let's enter it from outside and select between in the word comparator blocks option. Test it in simulation. When we start the simulation, we'll compare if it's within a range, say between 4 and 8. If these conditions aren't met, the output at INA input will be 1. The enable input must be active for this operation to take place. You can activate it instantly with a trigger or, as I have connected a high gate for this block to work regularly, we have added a block that continuously produces 1. Let's start the test. For example, we wrote the word value 5 between 4 and 8, and the output was 1. If I change this word data to 12, it will be outside this range and will revert to position 0. Next, we also made an analog comparator. This time, the INB input, INC input, was deactivated. The reason is that it will compare with a value. We set the value at 7.5. Here we entered the value from within the block. There was no need to connect any block. Let's perform the comparison operation together. When the analog input pulls the value above 7.5, the block output will be 1. I'm increasing it, and when I open it to 8, the output of the analog comparator block will be 1. Let's move on to our next blocks, the Again, we have word operation, analog, and long operation blocks for 3 different data types. First, let's see what can be done with the word operation block. With operation blocks, you can perform addition, subtraction, multiplication, division, XOR gate, left shift, right shift operations. On when trig is active, if this option is selected, with every rising edge on the TRG input on the block, specified mathematical operation is performed. Write on input, if this option is selected, the value at the INA input of the block and the value at the INB input of the block is processed. Result of the operation is written on the INA input of the block. A word register should be connected to the INA input of the block. This operation is performed at each PLC cycle by default. If on when trig is active option is selected, this operation is performed at each rising edge detected on the TRG input of the block. We can also look at these from the help section or programming guide. Here the details are given. In left shifting, when you say shift one unit to the left separating the values byte by byte, it transfers the value by shifting one unit to the left. According to the value coming to INB input, for example, in an arrangement of 1110, a circuit entered the INB input and shifted one unit to the left. As can be seen, the first unit was shifted to the left, and therefore a 0 was added to the right. In the right shift operation, similarly, if we consider dropping to the right, 3 we have a check bit operation. In check bit, as seen here, if the INB input is 8, it controls the 8th bit of INA. That is, you enter which bit of the incoming value will be controlled. Check the first one to shift left. Perform the left shift operation and control the first 0 bit. Check the first one to shift right. Shift right again and control the 0 bit. Check the last bit, the 15th bits, in left shift. Absolute value operation can be taken. For example, converting the output of -5 to +5. Bit compare. You connected two values to INA and INB, and you can write the output value according to the bits they compare with each other. You can perform the modulus operation. For example, you entered a number like 254. You entered the INB value of 10. While saying in-out, let me show it from here. Here, for example, in the operation, you write the mode and made the INB value 10. Depending on the value entered here, it will reflect the output value by taking the modulus 10. Let's do a simple application together. For example, let's do the multiplication of two values. Since we added a block to the outputs, it will prioritize the output. Let's do the value set operation. For example, we said 2, and when we made it 4, the output was transferred as 8 from 2 times. There are options such as write over the input and work when trig is active in the operation block. This works with this logic. When a value comes to the INB input, when the trigger is active, it writes that value to the INA input. Let's start the simulation. For example, when our value is 10. When we activate the digital input, it will write this value to the in-out input. And let's get the next value. 30, and again, as soon as digital input 2 is active. It will go over 10. And it will add this to the top of 10. And in this way, you can do the summing in one block. Where is it used? For example, if you do the calculation of cubic meters per second or liters per second in the INB input, you can add it regularly on a block by triggering a block per second. Or you can do a summing operation on an Let's continue to look at word operation here. What do we have? Low limit, high limit. I'll show you low limit here in the analog operation block in a bit. Merge A and B. The word value in the INB input is used to create a 32-bit data by combining the bits. Let's do this operation together. As a value, I enter 8. When we also entered 2 to the other, we displayed the value as 520. The reason is this: the input in B represents the 8th and 15th bits. The input in A represents the 0th to 7th bits. Thus, the value of 512 comes from 2 to the power of 9, and we got the value of 8 from 2 to the power of 3, so we transferred the value of 520 to the output. Let's continue. What else do we have here? We have our set value. The set value can also set the value directly on any word register block or by saying set by writing the block number. Let's look at these examples together. We showed the addition operation. Similar to the multiplication operation, it serves to sum two values in INA and in B values. Subtraction operations transferred multiplication 2 by 4 8 directly. Division operations are also available. And/or operations split the bits into, for example, 10 and 24 values. Wrote in binary and compared them with each other and converted. Here are the left shift, right shift operations. Bit control, lower limit, high limit. We said we'd do it in a bit. Merge A and B. By associating the value of two INA and in B inputs with each other, it converted 0 to 7 bits and 8 to 15 bits into a 4-byte, i.e., 32-bit data. Let's continue with the analog operation block. In analog operation, what operations can we do? If we go back to the beginning again, addition, subtraction, multiplication, and division operations. Absolute value, root extraction, sine, cosine, tangent, etc. Low limit, high. By the way, let's see the differences in arctangent in the explanation section. Trigonometric arctangent function. The other is also the trigonometric arctangent of in B over INA. Let's give an example of low limit. It is selected inside with low limit. Since I connected a block externally, I do not enter a value inside. Low limit serves this purpose. For example, we entered the value 80 and let's give the INA value in turn. When we give the value of 100, it will take the value of 100. That is, it will transfer any value change above 80 to the output. But any value below 80 will always transfer the value 80 to the output as it accepts the lower limit as 80. In high limit, similarly, it will transfer the value entering the in B input to the output at the exceedance of the high limit. No output process will be made above that limit in any way. Thus, we have completed the operation blocks. Let's look at the next structure. Up-down counters. We have two different counter blocks. Let's look at up-down counter 1 first as an example. I selected up in one, down in the other. I connected digital input 4 to reset the blocks. You can also determine the direction, whether it is up or down, from outside. Let's start the simulation. I'll get digital input 3 active. When I press it, the first trigger will be up, the other down by -1. It will start counting with each trigger received. One counts up, the other counts down. To reset the block, we will need to enter a value in digital input 4. When we activate digital input 4, a trigger came on the rising edge with reset inputs, and the blocks were reset. Our other block, up-down counter 2 block, can be used in both up and down counting. Let's exemplify this as well. Upward digital input 5. When we give a trigger, it performs an upward counting operation. When a trigger comes from digital input 6, it performs a downward counting operation. When a trigger comes to the reset input, digital input 7, it resets. Lastly, let's give an example of working time. Binary register is connected to blocks active in runtime block only works in online monitoring, so let's connect to the device via telediagram and upload the created project. I'm setting a value. I sent the binary 1 value, and as soon as it was active, it started counting. Let counting continue like this. By the way, let's provide this detail. If you can select the time measure as seconds, minutes, or hours, it has been This block has a permanent feature. The value continues where it left off as long as there is no trigger on the reset input of the block.